To continue now, we have to Professor Mauricio Sepúlveda introduce to Professor Oscar Jarrin. We can start, Mauricio.
Okay, thank you very much. It is a pleasure to present Oscar Jarrin, which is a colleague of my University of Concepcion. He came to Concepcion at August 2021. He's a recent colleague. His work is about partial differential equation in fluid mechanics, like Navier-Stokes equation, KdV equation, and the talk of this time now is a long time asymptotic for a damped Navier-Stokes-Bardina model. You can present your presentation, Oscar.
Okay, first, thank you so much for this introduction and for the invitation. I'm very happy to be here in this seminar. As already said, today I will talk about the long-time asymptotics for a damped Navier-Stokes-Bardina model. And this is a joint work with Fernando Cortés, an Ecuadorian colleague in the Escuela Politécnica Nacional. Okay, here's the plan of my presentation. First, I will introduce the equation, and then we will study the long-time behavior of weak solutions for this equation. And for this, we will use the tools of the dynamical systems, more precisely the notion of the global attractor. And then we will study some properties concerning the global attractor associated to these equations. Okay, so let me start by saying that the fluid motion is a complicated subject of the study from the mathematical and from the physical point of view. And it is well known that the Navier-Stokes equation given here is a good model to understand the fluid's motion. In this talk, we will assume the fluid on the wall space R3. Here in this the classical Navier-Stokes equations, we have that the velocity V and the pressure Q and there are unknowns of the systems. And moreover, we assume that we have an external force, which is a time-independent external force. It's this is a function vector which only depends on the spatial variable, and it don't change with the time. Here in the classical Navier-Stokes equation, we have two terms: the diffusion terms given by the Laplacian operator here, and the transport term, which actually is the more complicated term in the Navier-Stokes equation, given by the divergence of this product tensor, which intervenes the velocity v. Okay, we know that the Navier-Stokes equation is also a relevant physical model used in many applications as the oceanography, turbulence model, etc. However, the theoretical tools that we have to study this equation is not yet sufficient to prove the global well-posedness of the weak solutions. It's we can prove the existence of weak solutions, also called the Loret solutions, which belong to this functional space. There are bound solutions in time, square integrable solutions in space. Also, there are local L2 integrable solution in time and H1 solution in space. They also verify these estimates, also known as the energy estimates. We can construct these kind of solutions, but we don't know anything about the uniqueness of this solution. And this is one of the main open problems in the Navier-Stokes theory. And to overcome this big problem about the uniqueness of weak solutions, which are very used in all these physical relevant models, In the 80s, Bardina and his collaborators introduced this operator, which actually is a solution of this equation, also known as the Helmholtz equation. Moreover, as we can work in the wall space R3, we can actually define this operator as the convolution of the fusion phi with a kernel which has a very good decay properties. But the main idea of Bardina to introduce this kind of operator is to regularize the Navier-Stokes equation. Actually, if we apply this operator in each term of the classical Navier-Stokes equation, we get this regularized model. What is the idea? In the setting of this regularized model, we can prove the uniqueness of weak solutions, and this is the main motivation for Bardina to introduce this kind of operators. However, here we have a little problem. If we observe this system, we can see that this is not a closed system, in the sense that the new system does not depend only of the regularized velocity v and the regularized pressure term q, also depends of the original velocity v here in this term, in the nonlinear term. And in order to obtain a closed system, actually, we have the following simplification. The regularized nonlinear term can be written in this way. Here we have a rest term, which is defined by this formula. And once we have this formula, Bardina and Layton also suggest the following approximation for this rest term in order to write that the divergence of this regularized term also belongs that this divergence of this regularized velocity v. And with this approximation, we actually have the following closed term, which writes down only in terms in the regularized velocity v and the regularized pressure q. This is the well-known Navier-Stokes-Bardina model. And from now on, in order to simplify our writing, we are going to write the regularized velocity v as u, and we are going to write the regularized pressure q as p. Also, we are going to write the regularized external force g as an external force f. And then we get the following Navier-Stokes-Bardina model. Okay. Here, I didn't say we have this additional equation, the divergence of u is equal to zero, which corresponds to the fluid and compressibility fact. Okay. And also we have here the initial data to consider the initial value problem. Concerning the theoretical study of the Navier-Stokes-Bardina model, actually this is a recent study. In 2017, we have that Berzelli and Lewandowski used a variational formulation in order to prove the existence and the uniqueness of weak solution. This is the well point in the Navier-Stokes-Bardina model in this modification of the original Navier-Stokes equation, this additional term, also allow us to prove the uniqueness of weak solution, which in this case belong to this functional space. And they verify the following energy estimate. In this work, actually we're interested in studying the long-term behavior of these global in time weak solutions. And for this, if we get back to this energy estimate, we can see that we have this term t, and actually, if we take the limit when the time t goes to infinity, in the setting of this energy estimate, we lose any control, because this term, we can control this term here when the time t goes to infinity. And for this reason, actually, we are going to consider the following damped version of the Navier-Stokes-Bardina model, and we will introduce this additional term given here by a parameter beta, which is a parameter strictly positive, and the velocity u. And thus, from now on, we are going to work with this following damped version of the Navier-Stokes-Bardina model. So let me comment. This kind of damped term is also used in some physical settings. For example, in the study of the oceanography, we have many equations of this type, which consider this additional damping term. So once we have arrived to the question we are going to study, the first result that we have is the existence of global in time weak solutions for this damped version of the Navier-Stokes-Bardina model, and this is done in the following theorem. Here, we consider an initial data belonging to the space H1. We consider an stationary or time-independent external force, also belonging to the space H1. And we are able to prove that there exists a unique weak solution which belongs to this functional space. Actually, it's the same functional space of the classical Navier-Stokes-Bardina model without the damping term. But thanks to the additional damping term here, we also can prove the following energy control. Here, we may observe that this energy control actually makes sense only in the case with the parameter beta is strictly bigger than 0, thanks to this term here. But what is the idea to introduce these additional damping parameter? If we compare the original energy estimate, which has this term T here, and then if we compare the new energy estimate, we have a very good estimate thanks to this new damping term in the Navier-Stokes-Bardina model. Moreover, in this energy estimate, we have this quantity, the norm L2, plus the norm in the space H1 with this parameter, with little parameter alpha. And in order to simplify or write it, we are going to define this norm in the space H1, which is an equivalent norm only considering this parameter alpha. Okay, and in the setting of this damped Navier-Stokes-Bardina model, we have now all the tools to study the long-time behavior of solutions. So let me introduce some few notions we will use to do this study. First, the first key idea is the fact that as we have the uniqueness of weak solutions, actually we can define the following operator ST that if we take an initial data, the operator ST applied to the initial data is the solution arising for this initial data at the time t. And as I said, thanks to the uniqueness of the weak solution, this operator is well defined. And moreover, we can prove that this is a strongly continuous semigroup acting on the space H1. And here we can use the theory of the dynamical system in order to introduce the following definition, which concerns the global attractor associated to this semigroup here, and actually associated to the Navier-Stokes-Bardina model. So we will say that set A is a global attractor for this semigroup if this set is a compact.
Entonces en la noche vas a probar la pastilla y ya no tomas el otro.
Okay, if we say this is a compact set, it is a strictly invariant set. I mean, if we take any initial data belonging to this set A, then the solution which arises for all these initial data also belong to this set A. And moreover, maybe the most important characteristic of the global attractor is the following one, which, roughly speaking, we have that if we take any bounded set in the space H1, then we can find at time t, depending of this bounded set, that all the solutions arising for data belonging to this set B are closest as we want to the global attractor, in the sense that they belong to this neighborhood B of the global attractor. So in order to understand these this third condition in definition of the global attractor, we can see this draw here. If we think here we have an initial data in all our space H1, then when the time is big enough, we have that the solution arising for this initial data always belong to this kind of set, which actually is the global attractor. So our main result is to prove the existence of a global attractor associated to this Navier-Stokes-Bardina model, and this is actually the following goal of this theorem. Here, the proof of this theorem is actually a little technical. It uses some previous tools in the theory of the dynamical systems. But only let me say that the energy control due to this damping term is one of the key tools to prove the existence of this global attractor. We use this estimate, which actually is a very good estimate due to this exponential term, and this is very, very useful to prove the existence of a global attractor associated to these equations. And once we have the existence of a global attractor, then we are interested in study a more precisely descriptions of this global attractor. First, we are interested in study its fractal dimension, and moreover, we are also interested in study the internal structure of the global attractor. So, in order to understand what the fractal dimension is, let me present the following draw. Actually, this is a very simple idea. If we have here a regular set, and if we have to measure, to have a good measure of the size of this set, we can cover this part with balls of size epsilon. And the idea is that if we take this parameter epsilon smaller, we will have a better approximation. This is the idea of the box counting Hausdorff criterion. And using this idea, we can define the following quantity given by this expression here, which is also called the box counting dimension or the fractal dimension for this set here. So in our result, actually we prove an upper bound for the fractal dimension of the global attractor, which is essentially controlled by this constant, which depends on the parameters of the model. And which is more interesting, we have also here the dependence of the size of the external force given in this term here. So the main idea is that the size of the global attractor strongly depends on the size of the external force of the equation. Here we have also some open questions. For example, to study a better, a sharper upper bound, or also to study a lower upper bound for this fractal dimension of the global attractor, but this is possibly matter of further investigations. Okay, the other fact we are interested in study on the global attractor for the Navier-Stokes-Bardina model is to have a precise description on the internal structure of this set. And for this, we will use the following definition. Actually, this is an easy definition concerning the eternal solutions for the Navier-Stokes-Bardina model. So if we have an external force belonging to this space, we will say that the couple U and Q is an eternal solution for the Navier-Stokes-Bardina model if they belong to this functional space. Here, the word eternal means that the solution are defined for all t, positive and negative. Actually, this function is defined on the whole real line. And moreover, this is a weak solution of the Navier-Stokes-Bardina model. So here, once we have introduced the definition of eternal solutions for this equation, we can use a previous result, always in the theory of the dynamical system, who says that actually the global attractor is given by all the eternal solutions for the Navier-Stokes-Bardina model when the time t is equals to 0. In other words, in roughly speaking, the global attractor actually consists, as already said, in the set of functions which verifies this condition here at the precisely time t equals to 0. And then we have a very interesting remark. A particular case of eternal solutions which are defined for all times are the stationary ones. What is a stationary solution? Is a solution of the equation which does not depend on the time variable. It only depends on the spatial variable. And actually, this solution solves the following elliptic problem. Here, evidently, as they don't depend on the time t, we have the derivative in time is equal to 0, and then we have this elliptic problem. So the idea of the following result is to prove first the existence of these stationary solutions, and then to investigate their relation with the global attractor. So in the following theorem, we have that actually we are able to prove the existence of these stationary solutions. They belong to these Sobolev spaces. They solve evidently this elliptic problem. Moreover, all the stationary solutions verifies the following energy estimate. And the most interesting fact is that we have that all the stationary solutions belong to the global attractor. So if we get back to the picture of the global attractor here, we are proving that all the stationary solutions, the time independent solutions of the equation are all here inside the global attractor. Okay, so let me, okay. Moreover, we can go further in the study of the internal structure of the global attractor, and we can observe that all these results are valid for any parameter beta. However, if the parameter beta is larger than the size of the external force, let's say if we have this kind of control, we can also prove that in this particular case, the global attractor only contains the stationary solution, which moreover is the unique one. This is an additional result only concerning for this special case of the parameter beta, the damping parameter, which is larger than the external force. And in this particular case, which actually we have that all the solutions arising for any initial data will converge with the unique stationary solution of the Navier-Stokes-Bardina model. We can also derive a sharp asymptotic profile in time for these solutions. We can prove that this solution actually writes down as the stationary solution plus a rest term, which this rest term has the following estimates concerning the time. Okay, so this is all. This is a little presentations of all our results concerning this study of the long-time behavior for the Navier-Stokes-Bardina model, and I thank you so much for your attention.
Okay, thank you, Oscar. There is some question. No. Oscar, the question, the Bardina model, you consider the Bardina model in a dimension in three-dimensional case. Yes. There is some sense in two-dimensional case. It is possible to study that.
Yes, actually, in both case of dimension 2 and 3, we have a physical meaning of these equations. Also, there are previous work concerning these type of results from the global attractor for the dimension 2. However, for the dimension 2, we have the uniqueness of weak solutions for the classical Navier-Stokes equation. And in this case, I think is more interesting to study this kind of results for the original equations, for the Navier-Stokes equations in dimension 2. Here, we have to modify to regularize the classical Navier-Stokes equation following this idea of the Bardina's model in order to get the uniqueness of the weak solutions in the three-dimensional case. But in the two-dimensional case, we have the uniqueness of weak solutions for the classical equations. And I think actually we don't know to consider this kind of modification in the equations.
Okay, thank you. And other question, the damped term that you consider is have a mathematical sense, but it have a physical sense when you consider.
Yes, yeah. There is a some previous work in the oceanography studies. Actually, I don't remember precisely what is the exactly physical meaning of this damped term, but we have some references on this study. Actually, in this kind of works in oceanography, also in turbulence models. So it has a physical meaning.
Okay.
It has a physical meaning. Actually, in my PhD thesis, I work with this kind of damper terms, but also I consider another kind of damper term, which is actually a merely technical damper term in order to obtain a good energy estimates. But here we have chosen this kind of damper term, which also has an important physical meaning.
Okay. Another question?
Disculpe, una pregunta, one question.
Yes.
Yes.
Finally, there are open question about the Navier-Stokes because about the first, the unicity, and another open problem, open problem. I would like to know if you have information in this year, in last year, was solved the existence and uniqueness for Navier-Stokes equation.
Okay.
And I would like to know if you have some information about the solution in the long time behavior, about the stability. I would like to know stability when you have the damped. But for me, I don't understand the problem, the attractor, when you have the damped. I suggest, or I think that occurs only for some parameters. Bueno, en Spanish, yo pienso que estos problemas, claro, están dados por el beta, ¿no? Por el problema del sistema caótico, de este sistema dinámico, encajando como sistema dinámico, ¿no? Yo pienso que para ciertos parámetros de beta, pero lo que yo tengo las dudas porque tiene que ser para todo beta mayor que 0, ¿no?
Okay, so maybe I will answer in Spanish. Con respecto a resultados, bueno, sí, las ecuaciones estas ecuaciones de Navier-Stokes tienen muchísimos problemas abiertos y bastante complicados, empezando por el famoso problema del milenio. Con respecto a uno de los problemas que nos interesa aquí, que es la unicidad de las soluciones débiles, es un problema completamente abierto y en mi conocimiento no ha habido ningún avance importante en este sentido. Hay resultados en donde mediante condiciones adicionales sobre los datos, en definitiva pidiendo que los datos sean un poco más regulares, se puede mostrar también la existencia y la unicidad asociados para estos datos más regulares. Pero en el caso general, en donde el dato es una función cuadrado integrable y uno no supone nada más que eso, entonces el problema de la unicidad para estas soluciones débiles sigue completamente abierto. Y ese es como mencionaba antes, el objetivo de Bardina, regularizar, modificar un poco las ecuaciones mediante este operador aquí. Y con respecto a la segunda pregunta, si comprendí bien, bueno, para nosotros el objetivo es que el problema es que esta fuerza no depende de la variable de tiempo en este tipo de modelos que intentan estudiar el comportamiento en tiempo largo. La idea es que la fuerza que hace que el fluido se mueva es una fuerza que está actuando permanentemente. Y producto de esta condición de una fuerza estacionaria es que uno puede obtener esta estimación de energía que no es del todo buena si es que uno quiere tomar de alguna forma el límite cuando el tiempo va al infinito. Y entonces por eso nosotros introducimos este damping. Y efectivamente todos los resultados son válidos para cualquier término de damping estrictamente positivo. A excepción del último resultado que presenté, en donde si el término de damping en definitiva es suficientemente grande, en el sentido que debe ser más grande que el tamaño de la fuerza, que la norma de la fuerza, en este caso particular, podemos dar una descripción mucho más precisa del atractor global y en definitiva decir que el atractor global no es otra cosa que el conjunto que contiene únicamente la solución estacionaria.
Ok, muy agradecido. Many thanks again. Many thanks. Thank you for your answer.
Thank you for your question.
Muito obrigado, gracias.
Okay, muchas gracias. ¿Alguna otra pregunta? Other question? Bueno, creo que eso sería todo. Te agradecemos mucho, Oscar, por la presentación.
Muchas gracias por la invitación.
Thank you, Mauricio. Thank you a lot, Professor Oscar Jarrin, for your amazing talk.